What's up guys, it's the Unhinged Engineer here, and in case you weren't aware, you are going to learn a ton of math in aerospace engineering. And so today I thought it would be useful to break down the different subfields of math that you will learn in your engineering education that are actually going to be used the most in aerospace, as well as which subfields of aerospace are going to use those subfields of math the most correspondingly. As you're going about your mathematical journey and you're looking at what kinds of math you like and what kind of math you don't, and also as you're going along your aerospace journey and you realize what parts of the field you like and what parts of the field you don't, you can start to kind of pattern match, okay, if I like this part of aerospace, I should learn this kind of math more. Or if I like this kind of math, I might be more interested in this field of aerospace. You get the idea. In case you didn't know, I'm the Unhinged Engineer. I make professional development content for young engineers like myself. I'm an aerospace engineer by trade, but if you're just about anybody who's interested in professional development and kicking ass in your career, then this is definitely the channel for you. But enough beating around the bush. Let's get right into what kinds of math are actually used in aerospace engineering. So effectively, this video is going to be all about different kinds of math. Pretty much all types of aerospace engineering, if not engineering writ large, are going to use calculus in some way, and so it deserves its flowers for the first significant part of this conversation. So I'll break down what parts of calculus are used in what parts of aerospace. After that, we'll touch on linear algebra, which, while typically smaller in scope, at least for traditional engineering applications, I personally think is incredibly important, if not just as much as calculus. And then I'll end with some more advanced and niche topics that you might find interesting or might encounter on your journey and provide some context about how those are used. And for all of these, I'm going to break down not just what these fields of math are and what you'll learn, but also what types and fields of aerospace engineering that they're applied to the most or the least. So yeah, let's start off with calculus. So I'm going to start each subfield off with the Wikipedia definition just as a baseline here. So calculus is the mathematical study of continuous change. In the same way that geometry is the study of shapes, or algebra is a study of arithmetic operations and how you can refactor them, calculus is all about change. And there's two kinds of branches of calculus that are worth discussing here. One is differential calculus. So in other words, you're taking derivatives of or differentiating things and measuring rates of change. And the other is integral calculus, where you're using those rates of change and kind of initial conditions to determine accumulations of certain quantities over a span of time. That's integral calculus. Why do we care about calculus at all? Well, motion is all about change, and engineering in a lot of ways is all about motion. So if you're trying to study the motion of certain bodies or the behavior of certain quantities about your system over time, more likely than not, those quantities and bodies are going to be moving and changing, right? Their positions are changing, their velocities are changing, their accelerations are changing. And all of that change, the language we use to describe that mathematically, well, that's calculus. And that's why you would imagine calculus is so ubiquitous in aerospace engineering. And again, probably engineering writ large. What are the categories of calculus we're going to talk about here? The first one is Calc 1, which is just an intro to calculus, pretty much laying out the cast of characters and talking about differential and integral calculus, usually in basic applications and basic setups. After that, Calc 2 takes these concepts and focuses a little bit more on series and sequences. How do we take one of these functions that we're trying to approximate or take derivatives of and refactor it? You may have heard of something called Taylor series approximations or Maclaurin expansions you can see in the bottom right. These are all ways to use series and sequences of numbers or functions to describe the derivatives and the integrals we learned about in Calc 1. The third category of calculus worth discussing here is differential equations. Differential equations are effectively equations in which both the variables themselves and derivatives of those variables are functions of one another. So just to use a really basic example, you can see in the top part of this picture here, the heat conduction equation. So the first derivative of temperature with respect to time and the second derivative of temperature with respect to position, I would assume that's displacement along some plate or something, are in the same function as one another. So usually like you have a variable x and you have a variable y, but here you have a derivative of temperature and a second derivative of temperature in the same function. That's a differential equation. Now, what is the O and P here? O and P is the difference between ordinary and partial differential equations. So ordinary differential equations are differential equations in which variables are differentiated with respect to the same thing, right? So the same variables are differentiated with respect to the same thing. For example, if you have position and velocity and acceleration all in the same equation, velocity is the first derivative with respect to time and acceleration is the second derivative with respect to time, but position is the only variable in there, and time is the only thing we're differentiating with respect to. So it's an ordinary differential equation. However, in the bottom here, you can see we have temperature being differentiated against time, temperature being differentiated twice against position. So now we're differentiating against different things. That makes it a partial differential equation. So different classes will kind of bucket these different ways. Like sometimes they're separate classes, other times they're not. But nonetheless, all of these equations are used really, really extensively in engineering. Lastly, we're going to talk about vector calculus. So vector calculus kind of brushes up against linear algebra, but effectively it's taking these concepts of calculus and applying them to vectors instead of scalars, which again, we'll talk about the real substantive differences between vectors and scalars in the linear algebra section. But all you really need to know here is now instead of taking functions where you kind of have like an x and a y or an x and a t, and it's just like a two-dimensional plot, now we're doing volumes and hypervolumes even, and doing cool sorts of coordinate frame transformations while taking derivatives. You know, you integrate some kind of three-dimensional body to figure out its volume or its surface area or stuff like that. So it's much more geometric, it's much more linear algebra focused, but it's still the same core concepts of differential and integral calculus. Okay, so now that we've laid out the cast of characters, let's talk about their different applications. For the record, this slide, I'm going to use this template for pretty much every type of math that we talk about here, right? So on the left, I'm going to have the different kinds of math we're talking about. And on the right, I'm going to have like general buckets of aerospace engineering you might encounter. And if you watch my 10 different types of aerospace engineers video, you've probably seen kind of how these battle lines are divvied up previously. If you haven't, definitely check that one out. So let's talk about all these different fields of calculus. This is kind of a trivial one. Calc 1 is used in everything. Simple enough. It's the foundations of calculus. It's the most basic stuff. And there really isn't any field of aerospace engineering that I could think of that literally uses zero calculus. Moving on to calculus 2, things get a little bit more interesting. What I'm trying to get at here is that series and sequences are used a bit less in types of aerospace engineering that kind of don't do these expansions or these approximations as much or as intensely. So just as an example, if you're modeling motion with some kind of differential equation, we'll talk about numerical methods later. If you're doing that kind of thing, you may do something like a Taylor series expansion or whatnot, or Runge-Kutta approximation, which we'll talk about later. These are like concepts that use calculus 2. However, the reason I have them yellow and not green is because those are pretty basic. However, once you get into like finite element analysis or even like Kalman filtering or Bayesian inference stuff we'll talk about later, control systems theory, you get pretty crazy with the series and sequences you're modeling really quickly. So that's why I have those as green. Like a strong understanding of series and sequences is incredibly useful. That's why I have arrow structures there for the finite element analysis piece and guidance, navigation, and control there for kind of the statistical and the inferential / approximal piece there. That's where Calc 2 really comes in. Next part is differential equations. Differential equations is used almost as ubiquitously as Calc 1. Because again, typically where we're trying to model types of change, like you saw in that screenshot I had there, pretty much every field of engineering you could think of is going to have functions where derivatives are functions of position or time, or second derivatives are functions of whatever else, right? If you think about a particle or a moving body's like position, velocity, acceleration, also momentum and energy transfer, stuff like that, all of that can be described with differential equations, and so that's why it's incredibly important. And then lastly, vector calculus. This is a bit of a nit, right? But the only reason I have aerodynamics and propulsion listed as not using vector calculus here is because typically we kind of approximate things with cross sections of like an inlet or a rocket exhaust. Like we typically take a cross section of things and kind of measure across that cross section, whether it's pressure differentials or temperature differentials or stuff like that, versus in other fields we're really more interested in the entire volume of space that we're doing calculus with, especially like if you're doing, you know, anything to do with orbital mechanics, like which I have in aero and astronautics there, it gets pretty intense in terms of the three-dimensional vector calculus you have to do. So yeah, calculus is kind of like the mothership here. It's the biggest field of math that we're really going to use almost ubiquitously in aerospace engineering, and again, engineering writ large. Now let's get more into some of the more circumstantial ones you may or may not use throughout your engineering career. Okay, so starting off with linear algebra. Linear algebra is the branch of mathematics concerning linear equations, linear maps, and their representations in vector and matrix space. You may colloquially hear this referred to as matrix math, right? Why do we care about linear algebra? Effectively, the odds in actual engineering applications that we are only interested in a single value, aka a scalar, is incredibly low. Like usually we have multiple things that we're modeling at the same time, and when we have stuff like that, especially if there's a relationship between them that we can model linearly, we're gonna use stuff like like matrix math. Typically, when we don't have a relationship that we can model linearly, it's like a non-linear, difficult to quantify thing. One of the biggest concepts in aerospace engineering is linearization. How do I take this non-linear process and model it as a linear process, usually about some equilibrium point or whatnot, such that I can use the tools linear algebra provides me? Getting back to that projectile motion example, even if you're just modeling the motion in one dimension of one thing, say like position, so x, you also care about velocity and you also care about acceleration. So you can take those, you can represent it as a system of linear equations, and suddenly you've entered into linear algebra land. For something that simple, you probably wouldn't do it, but you can imagine that complexity increases pretty rapidly, and then suddenly you're using 9x9 matrices to describe state spaces and whatnot. So linear algebra, in my opinion, is incredibly important. And I want to make a separate video about regrets from my aerospace engineering degree, but spoiler alert for that. One of the biggest ones was that I only took one linear algebra class. And by the way, I took an advanced linear algebra class for math majors specifically that went really in-depth, more in-depth than most engineers, and even still, I don't think it was enough. I think linear algebra in general is neglected in contrast to its calculus brother, which sometimes can even be overdone. So I definitely think linear algebra is very important and worth discussing here. Okay, where is it used the most? Well, aerodynamics and propulsion, I kind of have listed not using linear algebra for the reasons I talked about earlier. Like usually we're taking some kind of cross section, and even if we're doing something like a partial differential equation, we're measuring it in one dimension, whether it's the outlet of a rocket exhaust or it's along some airfoil or something like that. Like usually we're representing things with respect to one surface, like curvilinear or not. Other fields though, aerostructures, GNC, they use linear algebra incredibly extensively. So aerostructures is the one I'm less familiar with. I'm much more familiar with GNC, but like when you're doing finite element analysis, you're setting everything up as this large matrix that has relationships and constraints between different quantities in this kind of physical structural system you're trying to model. You set that up as a matrix, and then by using finite element analysis, you're kind of linearly stepping around that matrix that you set up in certain ways to locally compute results for certain things. That's the whole idea with FEAs. If I can take this as a very arbitrary structure that is difficult to describe and it has this like non-linear relationships between different things, I can chop it up into small spaces or small elements, hence finite element. I can solve them up one by one and then ultimately get something that describes the whole body reasonably well by using smartly chosen linear approximation. GNC typically does a similar thing where if I have a control system and I'm trying to drive down some nonlinear process, I linearize it usually about some kind of stability or equilibrium point. I stabilize it about that, and then I describe it with kind of a linear time invariant system. This is also referred to as state space modeling. And so when you do that, again, even if your dynamics are nonlinear, you're using matrices and certain tricks you can do with matrices to solve for nonlinear processes and step them forward in time. So with FEA and the aerostructures example, it's more about stepping it throughout a structure, but in the GNC example, it's often about stepping it forward in time. And that could be in the guidance case, you're trying to like optimize some kind of path planning, and so you step forward, linearize, that's like sequential linear programming you may have heard of. And then control, it's like I have this nonlinear process I'm trying to control, let me linearize about a point, I do know how it behaves, and then kind of stretch that approximation out as far as I possibly can. Advanced concepts of linear algebra are really extensively used in these fields. The only reason I have aero and astronautics not listed as green here is really just that by the time it gets so intense, like the things we're talking about, you've usually entered into something like GNC more so than just raw aero or astrodynamics. So that's linear algebra. Super slept on in my opinion. Really interesting stuff, really cool. Advanced or niche topics here. I'm gonna start off with probability and statistics, which is not really advanced or niche. However, I do feel like the only thing that's probably neglected more so than linear algebra in this case is probability and statistics. Like I never even took a probability and statistics class in college. And as a guy who's doing like GNC stuff, AIML, that has seriously come back to bite me. So I've had a lot of catching up to do with probability and statistics. So if you're like me, you may not even have a class in your suggested academic plan about statistics that you can take, and so it's worth discussing here. Well, probability and statistics are different. So probability is the branch of mathematics concerning events and describing the likelihood of different events occurring, and then statistics is all about data. So collecting data, analyzing it, and inferring things from that data. I have in the bottom left a normal distribution there as an example of something you might see, which I'll have some cooler examples here in a moment. So why do we care about probability and statistics? Well, for the most part, Uncertainty is everywhere in the real world, and as engineers, we're incredibly interested in modeling real world dynamics. And so anywhere that you have some kind of uncertainty, whether it's about the process you're modeling or about the sensors you're getting information from, probability and statistics is going to be incredibly useful here. I have two examples. One on the bottom is kind of Bayesian inference with what's called a Gaussian process surrogate model. So we have this curve that we're trying to approximate, but we can only get discrete points of it. And by being smart about how we infer the behavior of this function based on how we're sampling it, then you can ultimately get a pretty good approximation of how it works. On the right there, I have a Kalman filter. We're trying to predict the motion of something using both a physical model, like of the dynamics of the situation that we have, as well as sensor measurements. The whole point of a Kalman filter is sometimes sensors go haywire and start giving you bad information, or sometimes dynamics change, right? Like if you're stalling out in an aircraft, the dynamics of how you're moving are going to change really, really quickly as compared to like being in cruise or pulling some kind of 9G maneuver. The dynamics of those situations and how you model them are very, very different. So if your model stops being accurate or your sensor stops being accurate, a Kalman filter helps you kind of discern between those two. That's why it's such a powerful and almost ubiquitous tool in aerospace. Anywhere that there's uncertainty, which is almost everywhere unless you're clairvoyant, then probability and statistics is incredibly, incredibly useful. Let's talk about numerical methods next. So numerical methods, or I have numerical analysis here to stick with the Wikipedia theme, is the study of algorithms for the problems of continuous mathematics. The second part here is more interesting. Typically use numerical approximation in addition to symbolic manipulation. What the hell does this mean? It's pretty vague. Numerical methods or numerical approximation is really just about all those fancy tricks I've referenced throughout this video. How do we actually use them to solve complicated, real-world, continuous variable mathematical problems or processes, right? I have on the bottom there a Runge-Kutta method, which is really just a more complex version of that Taylor series approximation or Euler method we discussed in the Calc 2 section. Like we're really just being a little bit smarter about how we differentiate and step for a process that we don't actually understand the dynamics of. So whether it's linearization, whether it's how do we actually solve for these things on a computer, numerical methods is all about that. Probably should have put this bullet up earlier, but numerical methods is really all about the quick and dirty tools we can use to model these processes accurately and efficiently. And something worth discussing here is the concept of a closed form solution. So typically, the simplest problems have a closed form solution, meaning you can pull out like a pen and paper, and you can move stuff around with algebra or calculus or whatever, and you can get like a closed form solution for this differential equation. This function is a solution to it. And then that means that I don't have to do any of these weird workaround processes that I'm referencing here. But 9 times out of 10 in the real world, that's not really the case. Or even if it is the case, a closed form solution is very computationally effective. And so we use kind of janky tips and tricks in numerical methods to solve them more efficiently. This is what numerical methods is all about. One of my favorite parts of engineering here that you don't really learn until the second half. I would say for the most part, the tools of numerical methods you're going to learn kind of in Calc 2, differential equations, and linear algebra. And then if you're lucky, like I was, you'll have a dedicated numerical methods class. Could also be called like applied math sometimes, that applies these concepts to physical processes we're trying to model or simulate. Last one I want to talk about here is signal processing, which has a place near and dear to my heart because actually my first job out of college had a lot of signal processing, which kind of freaked me out because I studied aerospace engineering and I didn't want to be an electrical engineer, but ultimately I warmed up to it for the reasons we'll talk about here. So signal processing is a field of electrical engineering, not aerospace, that focuses on analyzing, modifying, and synthesizing signals. So I have in the bottom here ways to compute the coefficients of a Fourier series, which I'll show you a graph of in a minute. But in other words, signal processing is all about electrical signals in electrical engineering. So it's relatively straightforward there. Why do we care? Many processes can be represented as signals, and thus signal processing gives us the conceptual tools, it's a very conceptual thing, to analyze and manipulate signals. So I have on the right here a box signal oscillating between positive and -1, and by using a Fourier series, we can actually approximate that function with a set of sine and cosine functions. And the more of them you use, the more accurately you can represent that box signal. You may be wondering, why the hell would you do that? Well, typically things are much more complicated than a box signal there. And also lots of physical processes tend to be cyclical. If you imagine in orbital mechanics, you're orbiting around the Earth, right? So the periods at which you have ground contacts with certain parts of the Earth, that's cyclical. The times at which you can point to the sun, you can collect power through your solar panel, that's cyclical. If another satellite is navigating relative to you, right, and clocking around you in some kind of way, or drifting drifting at a different altitude relative to you, that's going to be cyclical too. So in a lot of these physical processes that can be described by cycles, that means it can be described by signals, and thus signal processing is super, super useful for us. Okay, wrapping up here real quick. Let's talk about the areas in which these different fields are applied the most. Prob and stats is like kind of one of the more niche ones. I would really focus it on guidance, navigation, and control here, which again, in case it hasn't been obvious throughout this video, is the area that I hold the most near and dear to my heart in. I did a lot of study of these and have worked in them pretty extensively at this point. So guidance, navigation, and control use probability and statistics, kind of like with stuff like Kalman filters or Bayesian inference I showed you earlier. All these different aspects of GNC are going to use prob and stats very extensively, and thus it's kind of a shoe-in here. Numerical methods, aside from calculus and differential equations, is probably the one that's used the most ubiquitously, right? And linear algebra, like I didn't have listed as being used everywhere, mainly because the complexity of linear algebra stuff that you're gonna use is gonna fluctuate pretty dramatically. But with numerical methods, like even if you're just doing SolidWorks and you're just doing FEA and you're clicking a button, that is a ton of numerical methods. So numerical methods is incredibly useful for almost every kind of engineering that you're doing in which you're computationally solving for these processes or modeling / simulating these processes. Last thing here is signal processing. So the two I want to call out again are aerostructures and guidance, navigation, control. So GNC, with all these kinds of relative motions of certain things I talked about earlier, those are all cyclical processes that we could then model with signal processing tools. Simple enough. Aerostructures actually have here for a very specific part of it, and that's vibration modeling. So frequency response of physical bodies to some kind of shaking, the different modes of oscillation, and by extension like shear stress that you'll get in certain bodies, those are all modeled incredibly well with kind of signal processing tools, because we're modeling that vibration as like a sinusoid, and then we can approximate that with some kind of Fourier series thing and do all sorts of cool tricks to analyze, okay, what parts of this body are actually vibrating the most or have the most displacement, if there's constructive versus destructive interference in those signals. You can use a lot of really interesting signal processing tools for that in aerostructures. A pretty cool, like very niche part where signal processing is used very extensively. Okay, this was a bit of a long video. In case you didn't know, this is very similar to my what coding languages are actually used in aerospace engineering video. I just kind of wanted to run the gauntlet of all the different kinds of math that you are likely to encounter as an engineer, aerospace and otherwise, and for me as an aerospace engineer, take them and kind of section out, you know, which subfields of my discipline are they used the most in. So like I said in the beginning, you can kind of pattern match to say, oh, if I like this kind of math, I should look for jobs or research or whatever in these kinds of fields, or vice versa. If I'm interested in these kinds of fields, I should really study up on these kinds of math. And so that's where the idea for that table kind of came from. So if you found this interesting and or useful, I definitely would ask you to like, comment, and subscribe. I'm the Unhinged Engineer. I make professional development content for young engineers like myself. I make technical stuff like this. I also make career-oriented stuff about resumes and interviews and salary negotiations and everything else. If you are a young person trying to make your way in engineering like I am right now, I know it's pretty tough, I know it's pretty scary, but if you're looking to watch somebody go through that same journey at the same time as you, not 20 years ago, then this is definitely the channel for you. I'm the Unhinged Engineer. Please like, comment, and subscribe. Thank you so much for watching, and I will see you next time.